Okay.
Okay. So I guess I will restart. So this is the same overview slide. And so now let me dive into the main body of my talk. So like I said, the basic setting for our work is flux compactification of 2B string theory. So let me start with a short review. So string theory has supersymmetry in 10 dimensions. And to obtain a supersymmetric 4-dimensional effective field theory, you start with your 10-dimensional string theory and you compactify it on a Calabi-Yau threefold X. And the field content of the resulting low energy theory is determined by the topology of the threefold. And in particular, if you're working with 2B string theory in 10 dimensions, which is what we'll be doing throughout the talk, you have H21 vector multiplets and H11 plus 1 hypermultiplets, where H21 and H11 are the Hodge numbers that characterize the threefold. And so it's quite important for us that Calabi-Yaus can come in moduli spaces, which are a continuum of different complex structure on the same underlying real manifold. And the prototypical example of this is a torus. So the complex structure of a torus is specified by its modular parameter, tau, which lives in H mod SL2Z, so the usual keyhole region. And so in this talk, we're going to be dealing not with tori for the most part, but instead with Calabi-Yau threefolds. And we'll be viewing our threefolds as projective hypersurfaces. So I've given you an example of a threefold here. This is the octic threefold in 11222. And we'll be coming back to this example throughout the talk, like I said. So the moduli space of a threefold is an H21 dimensional moduli space. In the case of this example, we have two moduli, psi and phi, and the moduli space is these parameters, psi and phi, quotiented out by some global symmetries. And this is quite analogous to the torus, where your moduli space is the space of allowed values of tau, again, quotiented out by some global symmetries. And so each point in moduli space gives you a different Ricci flat Kähler manifold, so a different solution to the lower energy equations of motion.
Richard, I've got a question.
And, yeah.
In the previous slide, when you wrote down the polynomial, I think, are you going to set one of these deformations to 0 throughout the talk? And if yes, why would you not want to think of just one parameter family of solutions? Why do you want two parameter?
Oh, I just wanted to talk about the dimensionality of moduli space.
Okay, I see.
Indeed, I'm going to set psi equal to 0 for the rest of the talk, and we're going to have a one parameter moduli space of supersymmetric flux vacuola, which is what I was going to mention on this slide. Inside the two-dimensional moduli space, you can have one-dimensional slices where nice things happen.
Oh.
So thank you for the question. So while every choice of values of psi and phi gives you a Ricci flat Kähler manifold, not all of these are the same. And at positive codimension in complex structure moduli space, the resulting solutions can have some special properties. And the prototypical examples of this are the attractor mechanism and flux vacua. And what happens is at positive codimension in moduli space, one or more elements of integral cohomology has restricted Hodge type. And so usually that will make something interesting happen. If I give you a typical element of integral cohomology, like let's say an element of H3xz, it will in general have components along H3, 0, 2, 1, 1, 2, and 0, 3. But if, for instance, it has no 3, 0 or 0, 3 component, something interesting can happen. And that's what happens in flux compactifications. So 2B string theory has two form gauge fields called C and B with field strengths F and tau, as well as a complex structure, with the field strengths are F and H. And we have a complex scalar tau. And out of F, H, and tau, you define a complexified flux, which is G3, which is just F minus tau H. And so we're going to be dealing with flux compactifications where F and H have integral fluxes through X. And what that means is we just have some elements F and H of integral cohomology of X, and those are the fluxes. You pick them and analyze the dynamics of things subject to these fluxes. And so a choice of F and H, as well as dilaton tau, is said to define a flux vacuum at a point x star in moduli space if G3 is in H21 of x star plus H003. So you fix your F and your H, and you look for points in moduli space where at a generic point in moduli space, G3 will have components along 3, 0, 2, 1, 1, 2, and 0, 3. And then you look for nice points in moduli space where the 3, 0, and 1, 2 components vanish. And so, okay, if I have a point in moduli space where G3 is in 2, 1 plus 0, 3, the dynamics of the flux compactification are governed by a flux potential, which is just the integral of G3 wedge omega. So this is only sensitive to the 3, 0 part of G3. And so when W equals 0, we say supersymmetry is preserved. We have what's called a supersymmetric flux vacuum. And since W is equal to G3 wedge omega, a SUSY flux implies that G3 is just in H21. And that's a pretty restrictive condition. In particular, it's so restrictive that it doesn't just restrict the Hodge type of G3 itself, it also restricts the Hodge type of our integral fluxes F and H. So we have F and H in 2, 1 plus 1, 2. And so I want to emphasize that a priori, you might think this can't happen. If you actually count the number of conditions I need to solve to have G3 just in H21, it's an over-constrained system of equations. But despite the naive assumption that you can't solve over-constrained systems, indeed you can. There do exist supersymmetric flux vacua, and they can come either at isolated points in moduli space or in continuous families. So in this picture, I drew a line for a continuous family and little crosses for isolated points in moduli space, and you can have supersymmetric flux compactifications in either type. And so for most of this talk, I'm going to be dealing with continuous families because they provide us for a very rich example to study our conjectures in. And so this condition, FH in 2, 1 plus 1, 2, is quite analogous to the attractor equation. The attractor equation says that I have a charge gamma, which is in 3, 0 plus 0, 3. So instead of a charge in 3, 0 plus 0, 3, here I have fluxes in 2, 1 plus 1, 2. So we know that some attractors, rank 2 attractors, where we have 2 charges in 3, 0 plus 0, 3, have a rich arithmetic structure. We know this because of work of Moore and more recently work by Candelas et al. So in this talk, I'm going to ask the corresponding question about supersymmetric flux compactifications. Do supersymmetric flux compactifications enjoy any special arithmetic properties? Oh, and by the way, feel free to interrupt. I guess this is a fairly natural point to stop and ask for questions before I introduce arithmetic geometry, so I guess I'll pause for a second. Okay.
Just for confirmation, I have a question. So when you say the Hodge structure is a restricted Hodge structure, something, does it correspond to having a rational Hodge substructure?
Yeah.
The same thing.
Well, you really need, yeah. The answer is yes, but to go from statements of integral cohom, yeah, the answer is yes. Basically, the answer is yes. When a little later, we're going to pass from F and H of restricted Hodge type to Galois sub-representations of restricted Hodge type, which is closely related to your question. And there we'll need to invoke the Hodge conjecture. But I think the safe answer to your question is just yes, period.
Thank you.
Okay, so I have a question, which is that, so what type of physics motivations do you have to study arithmetic properties? Well, of course, this is a conference on number theory, so they themselves are interesting. But suppose that you have someone who is not interested in number theory per se. So
yeah, that's a great question. So unfortunately, I can't physically motivate doing the arithmetic geometry in the first place. But it's interesting that conditions like this that aren't phrased at all in terms of arithmetic end up implying things about the arithmetic.
Okay.
I wish I could tell you the reason why you should care about the arithmetic of freefolds is X, but that's a dream for now. Okay, so I guess I will proceed then. So I'm going to spend the rest of the talk talking about the arithmetic geometry of flux vacuola, which means I have to introduce arithmetic geometry. So I'm going to try to be fairly concrete, but I want to really explain what's going on clearly and with examples, because this is the setting for the rest of the talk. So far in everything I've said, we're viewing the Calabi-Yau threefold as an object in complex geometry. We've talked about things like the holomorphic threeform. So we're firmly in the land of complex geometry. But if we're going to ask about its arithmetic properties, we need a new point of view on geometry. We need arithmetic geometry. And in arithmetic geometry, you view some complex manifolds as varieties over Q. And that's a fancy word for saying I have a complex manifold which is defined as the zero locus of some polynomial. And if all coefficients of my polynomial are rational numbers, I can just view the whole polynomial as being defined over the rationals. And so in the simplest example, we start with a complex onefold, a torus, and we view it as being overdefined over Q. So we go from having a donut to what's called an elliptic curve. Tori are perhaps most naturally written as the Calabi-Yau onefold in P1, 2, 3. So by projectively setting one of my variables to 1, I arrive at what's called a Weierstrass form, which is y squared is equal to x cubed plus ax plus b. And so for my torus to be able to be defined over Q, what I need are the Weierstrass coefficients a and b to be defined over the rational numbers. Now, by a change of variables, we can clear the denominators of a and b. So we'll usually just take a and b to be integers, and then we'll be interested in elliptic curves of this type. Y squared is equal to x cubed plus ax plus b, where a and b are integers. Unfortunately, I'll probably in a couple slides go from calling these coefficients a and b to f and g, but in f and g, it would be y squared is equal to x cubed plus ax plus g. Okay. And so from a Weierstrass form like this, you define two important invariants, the discriminant delta, which is basically a cubed plus b squared, and the J invariant, which is a cubed over a cubed plus b squared. And so the J invariant is literally J of tau, where J is like, Q inverse plus 196,884 Q, and tau is the modular parameter of the complex torus. And the curve is non-singular unless this discriminant delta is 0. When the discriminant delta is 0, we have a nodal curve. Well, we have a singular point on our curve. It's not necessarily. So if I give you an equation of this form, where a and b are integers, you can reduce it over finite fields fp. So what that means is you literally just reduce a and b mod p, and then you plug in the values 0, 1, ... p minus 1 for x and y. And that's called reducing this equation mod p. And that's sort of what you do with curves in arithmetic geometry. You take their defining equations and you reduce them mod p. So the curve is smooth unless delta equals 0. So the resulting reduced curve will be smooth for all p other than the prime divisors of delta. And we say a prime p is good if the curve is smooth mod p, and bad if the curve is singular mod p. So importantly, once we've reduced over fp, there have to be a finite number of solutions. Over Q, there can a priori be a finite or infinite number of solutions. But over fp, there can only be a finite number of solutions because each of x and y can only take finitely many values. And so we call the number of solutions just number EP, where E is the elliptic curve and P is the prime. So for a random prime P, you sort of expect there to be P plus 1 solutions. The P is the P values we can plug in for X, and the 1 is the point at infinity that comes from the fact that we're really considering a projective curve. Now that's the expected number of solutions, but there's no guarantee that that's the actual number of solutions. So we define a scatter coefficient, which is the expected number of points minus the actual number of points. And so AP is P plus 1 minus the number EP. And the point counts AP are the basic objects I'm going to be considering for the rest of this talk. And in arithmetic geometry, basically what you do is you study these AP and you ask about what properties they have. And so the most famous result along these lines is the modularity theorem of Wiles et al., which says that for every elliptic curve E over Q, there exists a weight to cusp form Fe, such that for all good primes P, the point count coefficient AP of E and the B Fourier coefficient of the modular form are the same. Sort of more compactly, we have that point counts of on elliptic curves over Q give the Fourier coefficients of modular forms. And the precise type of modular form that appears in this way is a weight to cusp form for some gamma naught of n. And it's a weight to cusp form for gamma naught of n with some additional structure. It's an eigenfunction of the Hecke operators, which are some operators on gamma naught of n with arithmetic significance. And these are exactly the same modular forms, which we're later going to argue are associated to supersymmetric flux vacuums over Q.
Question.
Yeah.
What is n in gamma naught of n?
Ah, good. So n is the level. It's okay. Gamma naught of n is modular forms that are modular under the subgroup of SL2Z, where like C is congruent to 0 mod n. But you mean what is it in terms of the data of the curve? And it's called the conductor. It's a number that tells you what the bad primes are and how singular it is mod every bad prime. The formula for computing n is completely algorithmic, but it's somewhat complicated, so I didn't want to give the formula, but there's a known formula for elliptic curves. When we get to threefolds, the situation will be rather different, but for elliptic curves, it's completely algorithmic. Okay, so I suspect that not every physicist has seen this before, so I want to work through an example in detail. So I'm going to work concretely with the elliptic curve y squared is equal to x cubed minus 4x, which is an elliptic curve I picked randomly. So if you plug into these formulas, you get that delta is equal to 4096 and j is equal to 1728. So the bad primes are the prime divisors of delta. So the only bad prime is b equals 2. So for the rest of the talk, I'm really just going to ignore bad primes because things are complicated there. I'm going to restrict to good primes where life is simple. So the first good prime is p. So let's reduce over f3. Over f3, negative 4 is congruent to 2. So this elliptic curve becomes y squared is equal to x cubed plus 2. So if you plug in x equals 0, 1, 2, and y equals 0, 1, 2, you'll see that there are 4 points, 0, 0, 1, 0, 2, 1, or 2, 0, and then the point at infinity. So like when x equals 0, the right-hand side is 0, when y equals 0, the left-hand side is 0. Similarly, when x equals 1, 1 cubed is 1, 2 times 1 is 1, this is 3, 3 is 0, y is 0, we have a point on the curve, and so on. So A3 is P plus 1 minus the number of points over F3. So it's 3 plus 1 minus 4, which is 0. Now we can reduce over F5. Minus 4 is 1 mod 5. So this becomes y squared is equal to x cubed plus x. And again, we have 4 points over this curve. They are 0, 0, 2, 0, 3, 0, and then the point at infinity. And so now A5 is P plus 1 minus number of F5, which is 5 plus 1 minus 4, which is 2. So there is a unique weight 2 eigenform with rational coefficients for gamma naught of 64. And its first few Fourier terms are q plus 2q to the 5th minus 3q to the 9th, and so on. And so its third Fourier coefficient is 0, which is B3. And its fifth Fourier coefficient is 2, which is A5. And I've only checked 2 primes, but you can compute however many primes you'd like, and the pattern continues for all primes P. So the point counts for this elliptic curve give you the Fourier coefficients for this cusp form for all good primes. So that's what we mean when we say the elliptic curve is modular. I guess this is another natural stopping point. So are there questions here? Okay. This is basically the most concrete example we're going to have, but I thought it was important to show a hands-on calculation for what we're doing. But in everything I'm doing, I sort of swept one step under the rug, and it's a very important step. The step is the choice of rational model. So over C, neglecting Kähler structure, tori are entirely classified by J. And what that means is if I give you a tau, there's only one torus of that tau. That's not news to any string theorists in the room, but what is news to string theorists is that that's not true over Q. Over Q, there are infinitely many arithmetically inequivalent elliptic curves with the same J invariant. And to see why our usual complex intuition fails over Q, I think it's important to look at an example. So I'm going to give you an explicit example, which is consider these two elliptic curves. Y squared is equal to x cubed minus 4, and y squared is equal to x cubed plus 4. And so these curves, they both have a is equals 0, so they both have j equals 0. So they're isomorphic as complex tori. In this formula, if a is 0, j is just 0. So here a is 0 on both of them. So they both have j equals 0. But the map from this torus to this torus is generated by y goes to iy. Since there's an I in here, this change of variables isn't defined over Q. So even though they're isomorphic over C, they're not isomorphic over the rational numbers. And when this happens, when we have two elliptic curves with the same J invariant that aren't isomorphic over Q, we say they're different rational models for the same complex torus. And you can be pretty concrete. If you reduce these guys mod F7, this elliptic curve becomes y squared is equal to x cubed plus 3. And this elliptic curve just becomes y squared is equal to x cubed plus 4. And you can just compute A7 for these guys. And for this one, A7 is minus 5. And for this one, A7 is 5. So A7 is the Fourier coefficient of the modular form associated to these elliptic curves. So since they have different A7s, they're associated to different eigenforms. So even though we've picked a point in moduli space, we haven't specified enough data to concretely pin down a single modular form. We need to specify the extra data of a literal projective polynomial. So in string theory, we don't really do this. We work with things up to complex isomorphism, but to talk about arithmetic, you really do need to make this choice. And now I want to make a little aside. It's quite technical, but it'll be important later. So I want to comment briefly on the relationship between the eigenforms associated with two elliptic curves that are rational models for the same complex torus. So the technical name for the relationship is that we say they're related by a twist by a Dirichlet character. But that's a very complicated word for a simple thing. So let me explain what this simple thing is. So let's say we have two elliptic curves E and E prime that are both defined over Q and have the same J invariant. And let's write an for the nth coefficient of the modular form associated to E, and an prime for the nth Fourier coefficient of the modular form associated to E prime. Then we have, for all but finitely many primes, A prime is equal to plus or minus A. And the precise choice of signs is determined by the map between E and E prime. But away from these finitely many P, for any F and G that are related by the same way, it's the same choice of signs. So let me be a little bit more concrete by what I mean by that. So I'm going to talk to you about an important example, which is going to come back later. So let's say I have y squared is equal to x cubed plus fx plus g, and y squared is equal to x cubed plus fx minus g. So this is an example we're going to see later, so I want to go through it carefully. We have that for all but finitely many primes, AP is equal to the Legendre symbol of -4 over p times A prime p, where the Legendre symbol gives you a choice of plus or minus sign based on the parity of p mod 4. So if p is 1 mod 4, we get a plus, and if p is -1 mod 4, we get a minus. So in this example, 7 is 3 mod 4. So A7 has a relative minus sign in these two elliptic curves, which are related to g goes to minus g. But if I had computed A5 instead, I would have gotten that A5 is the same. And so the official name for what this is it's a twist by the Dirichlet character chi sub 4.b. But all that means is it means that the infinite number of minus signs are assigned according to this rule. So I know that was a lot of detail on what is basically a side point, but this particular example will come back later, so I wanted to have it out in the open.
Hi, Richard. Can I ask a question?
Yeah.
I may have missed this earlier. How is the modular subgroup related to the defining equation, and are the groups the same for E and E prime eigenforms?
Yeah. So so n, the level of the group, is determined in terms of the bad primes of E, and it tells you what the bad primes are and how singular it is over each bad p. Yeah, this is where I want to be. So n is determined by the bad primes and the badness of the reduction mod each p. And no, E and E prime will in general have different ends, different levels. And basically the reason why is, yeah, I can, so look at this example. If I remember correctly, these two have well, they probably have the same bad primes, but the singular points mod the bad primes in these two equations will be different. The exact points which cause the singularity.
Okay, thanks.
Mm-hmm. Okay. So before I move to threefolds from elliptic curves, let me say some words on a more abstract point of view on everything I just said. So far I've been fairly concrete. I've talked about solutions to equations, but like all good math, there's a more abstract point of view. So the middle cohomology of a 2n dimensional variety over Q furnishes a bn dimensional representation of the Galois group of Q bar over Q, which is the group of automorphisms of Q bar, the algebraic closure of Q, that preserve Q inside Q bar pointwise. So that's a bit of a mouthful, and it turns out the precise details of this group aren't super important to us. What is important is that you get a bn dimensional representation of this group. So for an elliptic curve, n is 1, so we get a b1 dimensional rep. b1 is 2, we have an a and a b cycle, and that's it. So we have a 2-dimensional rep rho 2 of E. Similarly, if I have a weight 2 cusp form, this is associated to a 2-dimensional rep rho 2 of F for the same group. And a more abstract but completely equivalent way of phrasing the modularity theorem is that for all elliptic curves, there exists a weight 2 eigenform F such that the two representations are the same. The content of the representation is basically the point counts. So this is just the same as the equation about the point counts, but phrased slightly differently. And so this is the language that working mathematicians in the field would typically use. And this is actually how we're later going to be able to connect to string theory. So this is my last slide on elliptic curves. So I guess I should pause and ask for questions.
I've got a question. So in the weight to eigenform that you take and you want to compute the point counts based on whatever the good primes are, is there an algorithmic formula which just tells you that given this good prime, this is going to be the Fourier coefficient, or do you really have to like sit down and expand the entire modular form?
Well, sorry. So the modular form is the modular form. It has its Fourier coefficients.
Yes.
The point counts come from the elliptic curve.
Right. My question is, okay, no, I'll ask you this later.
Is your question for each prime P, do you have to work out the number of points over FP by hand?
Yeah, kind of.
Well, sort of. So the first thing you would do is you would compute the conductor, which is the level n. And then you look up how many eigenforms there are for gamma naught of n of weight 2. And so let's say there's, I don't know, m eigenforms. You compute the AM for the first, you compute the AP for the first m good primes. Then you do linear algebra to find out what the actual eigenform is, and then you know the rest of the point counts from the modular form itself without having to look at the elliptic curve.
I see. So maybe let me rephrase the question. It might be a bit naive, but is there a way to like get out AP from the modular form without having to do the full Fourier expanded coefficients, but just looking at other AP primes where P prime are primes less than P?
If you have the eigenform as something like an eta quotient, maybe. But I don't know of a general way to do it. Okay. Maybe you could try to rig some sort of Rademacher or something. I don't know. I don't want to commit to Rademacher working on the spot, but yeah, I don't know of a way to do it.
Okay. Okay, thanks.
But what will, sorry. Sorry, let me say one more thing to Abi. Once you have uniquely pinned down the eigenform, you know all of the Fourier coefficients.
Yeah.
So in some sense, all of the information is contained in the first however many good primes you need to uniquely pick out an eigenform.
Right. No, the question is more computational. Is there a faster way to do it, kind of?
I mean, this is the algorithm I said makes you only check like a small number of P's, right? Yeah. For small n, there will only be a couple eigenforms. So you only need to work out like the first, I don't know, let's say 5 primes, and then you know the point counts for all the rest of them.
Right. Okay.
But for threefolds, this algorithm doesn't work because there's no algorithmic way of computing the level.
Right.
Okay, I think you had a question, Ashwin?
Yeah. So I'm quite interested in this work in terms of the Langlands correspondence. So I was wondering whether this rho 2 is related to the, there's a group related to the Galois group, which is the Weil-Deligne group. And in the Langlands correspondence, there's a homomorphism from this group to the Langlands dual group. In this case, it would be Langlands dual of, I believe, SL2Z. So is it related to this rho 2 representation you mentioned?
It's all related. These Galois reps are the sort of the starting point for the Langlands point of view. But I don't want to be particularly Langlandsy, since I think for this level of talk I can say everything I need without invoking Langlands terminology. But yeah, it's a 2D rep, which is where SL2Z comes from, and then you could look for like higher dimensional reps, and then you would need SL3 and SL4 and so on.
Thank you.
Okay, then I guess I will start talking about threefolds. So as we all know, tori are Calabi-Yau one-folds. So it's quite natural to ask whether this can be generalized to higher dimensional Calabi-Yaus. And so the modularity of higher dimensional Calabi-Yaus, including in particular Calabi-Yau threefolds, is an active area of research. So I've given you 2 fairly recent reviews here, but the field is very much in development. So if I'm going to talk about the arithmetic of threefolds over Q, I should tell you what a threefold over Q is. So for the purposes of this talk, I'm going to think about a threefold as the zero set of some projective polynomial. And if all of the coefficients in my polynomial are rational, I'll say that defines a threefold over Q. So like in the example I've been showing you, if my coefficients psi and phi are rational, I say that defines a threefold over Q. And so the modularity and arithmetic of threefolds over Q is technically a much harder problem than elliptic curves. There's sort of many reasons why a not especially profound problem is that computing the actual point count coefficients is quite hard for threefolds in general. If you're trying to do a brute force approach, I mean, you need to have your computer spend a long time thinking about it. But the real reason why it's hard is the associated Galois rep is now B3 dimensional. So it's 2 plus 2 H21 dimensional. These Galois reps are quite high dimensional for generic H21. And we really understand Galois representations best when they're 2-dimensional. In fact, there's a theorem that says that every 2D Galois representation with the appropriate adjectives has to come from an eigenform. For higher dimensional Galois reps, there's no such theorem. We don't know what the right sort of modular forms, what sort of automorphic objects we should be looking for inside the point counts. And so not surprisingly, the best known results for threefolds happen for rigid threefolds, which are threefolds with H21 equals 0. When H21 equals 0, B3 is just 2. The whole Galois rep is 2-dimensional, and we can use results similar to those that were developed for elliptic curves. And there's a theorem by Gouvier and Yui, which says that rigid threefolds over Q are modular, and their point counts give you the Fourier coefficients of weight 4 eigenforms. And basically the proof goes as follows. They proved the result I said before, which is that they proved part of a general program, but anyway, they proved that all 2-dimensional Galois reps of the right type to be associated to a rigid threefold are associated to weight 4 eigenforms, which just implies that the point counts of a rigid threefold give you the Fourier coefficients of a weight 4 eigenform. If H21 is not 0, you're not quite out of luck. You can sometimes get a 2-dimensional Galois rep out of a higher dimensional Galois rep if the Galois rep is reducible. So if I have my high dimensional Galois rep and it turns into a 2-dimensional piece plus a 2 H21 dimensional piece, you can study the 2-dimensional piece directly. And in some cases, rho 2 can be related to the Galois rep of a weight 2 eigenform, and then we say that the threefold is weight 2 modular. Its point counts give you the Fourier coefficients of a weight 2 modular form in a way very similar to how elliptic curves did. So when does this happen? If I give you a generic threefold, a highly non-generic threefold, what are the exact type of non-genericity conditions that make its Galois rep decompose into a piece that looks like a weight 2 eigenform? That happens whenever there is a 2-dimensional subspace of H3XQ, the singular cohomology with rational coefficients, where everything in this subspace has Hodge type 2, 1 plus 1, 2. And that's great, because as I told you, this always happens in supersymmetric flux compactifications. Our integral fluxes, F and H, are in 2, 1 plus 1, 2. So if you define the Q span of F and H, we call it H flux. You have a 2-dimensional subspace of H3XQ. The results from the last slide kicks in, and we have our main result, which is that, subject to some technical assumptions, supersymmetric flux compactifications over the rational numbers are modular, and their point counts give you the Fourier coefficients of weight 2 cusp forms. And this is a very good point to mention that a similar argument shows that rank 2 attractors over Q are associated to weight 4 cusp forms. But for this talk, we're going to be talking about flux modularity. So we'll be interested in examining whether supersymmetric flux compactifications over Q really are modular.
Sorry, one more question.
Yeah.
the statement that SUSY flux compactifications are over Q or like associated weight to cusp forms. Is that a statement that you make because you've checked through the entire space of cusp forms or constructed the weight space of cusp forms and then checked for a large case of SUSY flux compactification, or is it just this one?
No. So there is an abstract argument, okay, but it depends on things like the Hodge conjecture. So we wanted to check it in an example.
I see.
Yeah, so there's a general statement that's true regardless of this example. But this example actually provides us an infinite number of examples to check whether our conjecture holds or not.
I see. Okay. So then this conjecture is based on the one example you showed right now.
No, we made the conjecture before we knew about the example.
Oh, I see.
In fact, we almost published just the conjecture in like a 3-page paper, but then we found an example where the point counts were known.
I see.
I just the argument on this page. The technical assumptions are in going from this 2-dimensional subspace of H3XQ to a 2-dimensional subrepresentation. It's quite non-trivial to actually argue that the rep decomposes. You need this thing called the Hodge conjecture, which is a Millennium Prize problem. So since there's some very high-powered math going on behind the scenes, we wanted to check things in a concrete example, but we had the conjecture way before we knew the example where we could actually see anything explicitly.
I see.
Can I ask a quick question?
Yeah.
Don't you also expect that there are a bunch of not supersymmetric flux compactifications over Q that are also modular? Like, is there some expectation that all CY3 folds over Q? Or
sorry, finish your question.
Yeah, I was just wondering if there's like if there are any points off of this psi or phi, I forget which, equals 0 sublocus where you expect the Calabi-Yau threefold to be modular, but for it to not, I mean, it's not going to be generically a supersymmetric flux vacuum.
So there's, I'm not sure what level you're asking the question. There's the generic Langlands program, which basically says we expect every variety over Q to be associated to some sort of automorphic object. So that's quite high-powered math, and I'm going to leave that one alone and just talk about things whose point counts have a literal weight 2 cusp form. So no, you're completely correct. Not everything that is weight 2 modular in this way is a supersymmetric flux compactification. But if I just give you a list if I just say I just give you the point counts for every rational variety in a moduli space, now I've told you which ones you can definitely look at and find point counts. I haven't said anything about all weight 2 modular threefolds or supersymmetric flux compactifications because that isn't true. There are lots of ways you can get the Fourier coefficients of weight 2 eigenforms, but this is a way that guarantees it.
I see. And yeah, I guess maybe I'll ask you afterwards, but I guess I'm just confused because it seems like you have supersymmetric flux compactifications that aren't defined over Q and hence aren't modular. And then conversely, you have things that are modular and not supersymmetric flux compactifications. So these two notions seem like they overlap in some cases, but otherwise are like sort of distinct. But
right, but they're distinct. But they're distinct in an interesting way, which is that when I have both of them, something interesting happens. If I have a SUSY flux and it's defined over Q, then something interesting happens. Okay. You could just as well say, well, there are lots of points in moduli space that are defined over Q. And that's true, there are, but I don't know anything about the modular properties of most of them. I have identified a subset of them where I know the modular properties.
I see. Cool. Thanks.
Mm-hmm.
Sorry, what was small f, lowercase f, lowercase h?
Oh,
sorry,
these are the fluxes.
Capital, same as the capital.
Capital F are the fields and little f are the actual elements of H3XZ.
Ah, okay, class.
Yeah.
Okay. And one more thing. So this statement is implied just from Hodge conjecture?
Sort of. So the Hodge conjecture, says that if I have this, I have a two-dimensional Galois rep, a two-dimensional rep of the Galois of Q bar over K for some number field K. Now, when K isn't Q, in general, I don't know anything about these Galois reps, but when K happens to be Q, then it has to be weight 2 modular. So there's two assumptions at play. One is the Hodge conjecture, and then there's the other assumption that this number field K equals Q. And unfortunately, I don't know a way to check that second assumption short of checking it for each individual example.
Okay, thank you.
Mm-hmm. In some sense, that one is the more annoying conjecture. As a physicist, I'm happy to assume the Hodge conjecture and just say it's some fancy math. It's probably true, but this we call it the splitting field conjecture. It's quite important for actually getting modular forms. But this example that we're going to talk about, we've checked some millions of number of cases on a computer, and the K is always Q. So when K is Q, then Hodge is enough to imply modularity.
Okay, thank you.
Okay. Yeah, okay. So I'm going to spend most of the rest of this talk talking about this example. So like I said, whenever psi equals 0, we have a supersymmetric flux compactification. And so then if I pick phi to be rational, I have a supersymmetric flux compactification over Q. And we expect to have the Fourier coefficients of a weight 2 eigenform inside the point counts. Now, computing the point counts for this threefold is hard. But fortunately, someone did it for us. It was computed by Shabnam Kadir in her PhD thesis. So we can just look up the point counts and hope to find the Fourier coefficients of weight 2 eigenforms. And we do. Here I've given some representative choices of phi, and for each phi we find a weight 2 eigenform. So this way of labeling weight 2 eigenforms is called an LMFDB label. So the first number is n, the level, the second number is the weight, and then the last two just tell you which modular form of that weight and level you have. But the point is here, I think we have order 10 points where you can just look at the Fourier coefficients and see, or look at the point counts and see that they really do have the Fourier coefficients of the weight 2 eigenforms. So we call this strong evidence for flux modularity. So there's an obvious question at this point, which is that what's the physical interpretation of everything I just told you? While I wish I could tell you the answer, I don't know. I don't have a good physical motivation for computing point counts. But since these same weight 2 eigenforms are associated to elliptic curves, maybe a good starting point is finding the associated elliptic curves somewhere in the geometry of the string theory. And so an excellent hint in this direction comes from the fact that in addition to picking fluxes, you need a dilaton tau. And so tau lives in H mod SL2Z, so you can really think of it as the modular parameter of some course. And this is basically the point of F theory.
Sorry, yeah. Can you maybe just scroll back to the LMFDB labels real quick?
Yeah.
Okay, thanks.
Yeah, so you can go into LMFDB, type in this label, and it'll give you the AP.
Okay.
It won't quite be the AP for the threefold. It will be the AP for the elliptic curve, but the AP of the threefold is a little more complicated. So
yeah, because I just want to find out that the I was just saying, because like the phi equals 9 case, I think there's also like a hypergeometric realization of these things, and I think they also show up in Professor Ling Lang's talk.
Yes, this is quite related. I mean, Professor Ling Lang's talk was about when hypergeometric motives are decomposable. Right. That's exactly what we're seeing here. We're having our motives become decomposable.
Right.
I strongly suspect that a lot of what I'm saying here can be derived in an alternate way from something like what happened in her talk.
Yeah, and she's here, I think, in this thing, so maybe she might have a comment later. So if I understand that, you're saying that you could write this in a hypergeometric fashion.
Well, I don't know how to do it, but I know that the period.
Oh, yeah.
Yeah, you can write it in terms of hypergeometric functions.
Okay, thank you.
So the periods on this locus of moduli space are pretty much just hypergeometric functions. And my guess is those hypergeometric functions have something like a Whipple formula, and then something like what you talked about in your lecture could then kick in to reproduce this from a different point of view.
I think probably not Whipple, but some other decomposition going on. Yeah.
Yeah. Okay. I don't know exactly what the decomposition is, but something like that I think should apply. Yeah. Okay. Right. So so the dilaton tau is the modular parameter of some torus. The torus is the generic fiber of the F theory uplift. And indeed, you can check that the dilaton really is the tau of the elliptic curve associated to the modular form. Remember, each tau is associated to an infinite tower of elliptic curves, but each eigenform is associated to like some finite set of terms. Okay, so in our example, the octic Calabi-Yau in P11222, you can compute J as a function of phi, where by J of phi, I mean J of tau of phi, where tau of phi is the dilaton that makes G3 have restricted Hodge type. And indeed, you see that for each rational phi, you get a rational J. So you could hope that there is some elliptic curve that is reproducing the modularity.
Is this in the examples or in general?
So this is in the examples. So for the rest of the talk, I'm going to be talking about examples. We're currently trying to understand this part of the talk abstractly without having an example. But yeah, we've now gone from the things that I think are always true to things that I really can only justify in some example.
May I ask one more question?
Sure.
You're muted, Tyson.
Sure. So my question is whether the tau is algebraic or not. Whether it is the root of a quadratic polynomial or not.
So we have a whole parameter of a whole one parameter family. Of course, for generic phi, it doesn't have to be. I think for rational phi, there is some algebraicity constraint, but I don't know off the top of my head. I think the answer to your question is yes, but I couldn't prove it for you if you put me on the spot. I know we talk about this in Appendix B of our paper.
The earlier paper on October.
Yeah.
Maybe well, later. Let's talk about it.
Yeah. Okay. So in F theory, we have an explicit Weierstrass form corresponding to tau, which was constructed by Sen. So for a supersymmetric flux compactification, it takes the form y squared is equal to x cubed plus c minus 3x plus c minus 2, where c is at this point an arbitrary number. But j of this elliptic curve is determined by c. So if you set j of c equal to this j of phi, you can solve for c as a function of phi, and you get 9/4 phi squared. So for each phi, plugging in c of phi, we get an elliptic curve over Q with the right J invariant to potentially reproduce the modularity we've seen. And so I've only talked about the example of the threefold in 11222, but at this point, everything I've said can be checked in several other examples. And so you might think we're done. For each rational phi, we have a rational elliptic curve, and it has the right J invariant, but that's not enough. We don't just want an irrational elliptic curve, we want the right rational elliptic curve. And unfortunately, these curves are not the right ones. If you plug in, say, phi equals 2, you can look up the modular form associated to this elliptic curve, and it isn't 192.2.8.a, it's something rather more complicated. So we'd like to do a little better, and we can. And to see why, it's instructive to take the limit of phi goes to 0. And as phi goes to 0, this equation that we got from following Sen blows up. We have a 0 in the denominator and we get bad infinities, but nothing's actually singular in the threefold or in the fourfold. This is basically a coordinate singularity, and you can get out of it by redefining coordinates. So if you define y goes to square root of a times y, you get an a squared in the f term and an a cubed in the g term. Now, from the point counts, we know that phi equals 0 corresponds to the eigenform 64.2.8.8, which is associated to the elliptic curve y squared is equal to x cubed plus x. So if you put in this elliptic curve by hand at phi equals 0, that is, you pick a such that the limit of this equation as phi goes to 0 gives you this elliptic curve, then you will have a family of elliptic curves that have the right j for each phi and give you the right modular form at one point. So you can do that by picking a of phi is equal to 2 over 3 phi. So then if you plug that into this equation, you get this family of elliptic curves. And so this family of elliptic curves is very nice. For all rational phi, it has the right rational j invariant, and it's defined over Q for all rational phi. And at phi equals 0, it gives you the right modular form. But it's even better. It gives you the right modular form for all phi. We've checked some number of low single-digit millions of examples, and it gives you the right modular form for each of these examples. So by putting in by hand one choice of rational model at phi equals 0, we get out the rational models for all other rational phi for free from this F-theory construction. So that's pretty neat. We've put in one point of data and gotten out an infinite number of other points of data. And I was fairly surprised when we saw this. And the reason why I was a little bit surprised when we saw this is that F-theory doesn't a priori know anything about the rational numbers. If you read the construction of F-theory, nobody talks about anything being over Q. Everything is defined in terms of periods and things of that nature. But even though there's no arithmetic built into F-theory by hand, it suffices the F-theory analysis to give you the right rational models for all other phi. And it can actually make predictions. To see why, let me give you a little puzzle. So the Calabi-Yau threefold we've been talking about has a symmetry under phi goes to minus phi. This is a symmetry of moduli space. But on the other hand, these elliptic curves, they don't have this symmetry because this term is odd in phi. And in particular, under phi goes to minus phi, these elliptic curves basically do g goes to minus g. So under phi goes to minus phi, we get a different modular form. And so why doesn't this symmetry extend to the arithmetic? Well, at the level of the threefold, one way you can implement phi goes to minus phi is you can take x1 goes to e to the I pi over 4. Sorry, there should be an x1 in here, but you rescale x1 by e to the I pi over 4, and that just does phi goes to minus phi for you. But importantly, this has an I in it, so it's not defined over Q. So this complex symmetry doesn't extend to the symmetry of the arithmetic. Put another way, phi goes to minus phi takes us between two inequivalent rational models for the same threefold. This is the rational model we've been working with, but we could have picked this other rational model, and these two rational models are related by the complex symmetry phi goes to minus phi. And these elliptic curves, their transformation under phi goes to minus phi predicts the modular form associated to this rational model from the modular form associated to this rational model. And the reason why is simple. So if you think about our earlier example of y squared is equal to x cubed plus fx plus g, and y squared is equal to x cubed plus fx minus g. So the associated modular forms are related by twisting by this 4b, which is just the thing that gives you a minus sign if q is 3 mod 4 and a plus sign if p is 1 mod 4. And so since phi goes to minus phi acts as the curve on the curves as g goes to minus g, if we take seriously the idea that the modular form associated to the threefold has to be the one associated to the elliptic curve, then this tells us what the relative twist between the threefold, between the points phi and between these two eigenforms for any fixed phi has to be. they have to be twisted by this chi sub 4b. And for every point we've checked, it's true. The modular forms associated to these two rational models at the same point in moduli space are related by this twist, as exactly follows from the F theory. So what we're seeing really is that the F theory picture of these flux compactifications doesn't just reflect the complex geometry of the threefold, it also reflects the arithmetic geometry of the threefolds. So that's all I wanted to say. Let me just recap briefly. So string theory is usually framed in complex geometry, but there's another very exciting point of view called arithmetic geometry. And so what we set out to do was relate this to physics. And we argued, subject to some technical assumptions, that supersymmetric flux compactifications over Q are modular. And so I still don't know why this should be true physically. I don't know what point counts mean physically. But I think that the fact that F theory really does reflect this arithmetic structure is a strong hint that there is something there. And so I would like to hope that this is an early sign of a relationship that we can develop between string theory and arithmetic geometry that hopefully can reproduce the successes string theory had in informing and being informed by complex geometry. And I always like to close my talks on an optimistic note. So let me just say that a dream outlook for this field would be a physical interpretation of the Fourier coefficients AP. So that's what I wanted to say. Thank you very much for listening. And again, thank the organizers for inviting me.
Thank you very much for the very interesting talk. Are there questions? Please unmute yourself and ask or raise hands.
Hi, Richard, just want to say that when you go back to your threefold model, for the two choices of the parameter phi and minus phi, actually in mirror symmetry, when they go to the mirror, they change the parameter. Here, I think likely it's from phi to the minus 4. So they will correspond to the same mirror. You can actually see over there, they will give you the point counts for the Calabi-Yau threefold will be more or less the same if you change the phi to minus phi. It's relating to somehow to the mirror symmetry. I mean, the way they do mirror symmetry by quotient out the finite group action.
So I think I agree that for the mirror they should have the same point counts, but you can just literally look up the point counts that have already been computed, and indeed the points phi and minus phi don't have the same point counts. They're closely related, but they're not the same.
They made the major term. I think they will share the same major term.
Yes, they certainly share the same major term, but the bit that comes from this weight 2 eigenform, that bit picks up a minus sign.
Yeah, for the elliptic curve, indeed they're different by a quadratic twist. All right.
But even in the threefold, you can compute the major term and then the subleading term, and the first subleading term differs under phi goes to minus phi.
So that, yeah, I mean, literally if you count that way, but that the discrepancy disappear when, I mean, you go to the mirror or you go to the quadratic extension, whichever way you call it. I mean, in terms of picafoots, in that regard, they are actually pretty similar.
They're very similar, but I mean, you can fix a prime p and look up the zeta functions for phi and minus phi, and they really do have this relative minus sign in the zeta function.
Other questions?
May I ask a question? I'm not sure whether this is a question to Richard or Ling. When we set the value of psi to 0 and phi equal something at the rational values, and then the period integrals and the first derivatives and second derivatives stuff will be given by hypergeometric functions. And do we have a reason to expect that their values or ratio of those values are algebraic?
Typically, I mean, the way the period, depending on the structures, there are classifications of hypergeometric kind of, if you have hypergeometric function, and one extreme will be the hypergeometric function turn out to be algebraic. So this is a very extreme case. But the other extreme will be likely they are all linearly, algebraic. They are linearly independent over a Q bar. So typically that's what will happen. And regarding modular forms, only in the cases you look at modular function when tau is imaginary quadratic number, the J value is algebraic. Otherwise, it's always transcendental.
Mm-hmm.
Yeah.
Right, thank you.
More questions? If not, let's thank the speaker again. Okay, so we resume as in the schedule.